Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 6.1.5, dimension of the kernel and the range. Okay, so what is the kernel? The kernel of a map is the same thing as the preimage of zero. Okay, the preimage of the zero additive identity, which is kind of what we were talking about. In fact, we were discussing preimages of zero up here. So this would be like the kernel. This would be the kernel of one Smith normal form. That would be the kernel of the other one. Now, the nice thing about the Smith normal form is if you look at the dimension of the kernel, so the dimension is just the measure of freeness, of how many things you have in your tuples. So if you look at the kernel, the dimension of the kernel, the dimension of the range of the Smith normal form, because you had isomorphisms running before and after the map, you can kind of pull them back isomorphically to actually get the same dimensions of the kernel and the range for any map at all described by a matrix here. So, so that's kind of nice. All right. So, for instance, well, how do you think about the Smith normal form then? How do you find the kernel and the range dimension? Well, here's a little example here. Notice that the Smith normal form represents a map that sends, this one in particular, sends, it looks like it has domain R5 and codomain R3. What if it's range? What is range? Range is the full image of the domain, like where things actually hit. Not all the codomain is necessarily hit, but the range is everything that is hit. Notice what's hit here. E1 goes to E1 and E2 goes to E2. Everything and all the other standard basis ones, E3 and E4 and E5, actually end up going to 0. So what is the range? It looks like everything in the output of the function really is in the land of multiples of E1 added with multiples of E2. Notice that's represented by how many ones you see right here. This is the range dimension. The kernel dimension, well, what's heading off to 0? Well, quite literally, E3, E4, and E5 are heading to 0. And that's the kernel. The kernel dimension is, well, there is the span of those guys right there, which is 3. So we can actually get the dimension of the kernel and the dimension of the range just by counting numbers of columns. Now, the number of columns represent the dimension of the domain itself. Notice that the kernel dimension plus the range dimension will be equal to the domain dimension here. So it's easy to kind of read off the kernel dimension, the range dimension. In fact, just as we made this computation up here in the last subsection, here when we were finding the preimage of 0, we noticed we figuring everything in the domain that gives us a 0, and we noticed that A and B had to the A and B are necessarily 0 here but this guy could be C could be anything you wanted right here. So A and B were necessarily forced to be 0 if we're heading to this point, but C could be anything. We actually computed that and we found the dimension. So this is the actual kernel itself has to be this, which is the preimage of 0. And notice we just get that. That happened to do with the number of columns that were zeros. So from a computational standpoint, it's pretty clear to see what the dimension of the kernel is from the Smith normal form and the dimension of the range. Very, very simple. So if we just given any kind of map at all, at first, if we don't have the Smith normal form, we don't know what the dimensions are of the range and the kernel. But the Smith normal form isomorphically tells us what the kernel dimension is, what the range dimension is for any map. So it's one nice use of the Smith normal form. So let's look at the different types of Smith normal forms that we could get for a matrix that's a size 3 by 5. So we have ones down the diagonal as far as we can go. or you could have ones down to that point, or a 1 to that point, or just everything 0. Notice in this case, the kernel, there's 3 0 columns, the dimension of the kernel is 3. Here, there's 2 non-zero columns, dimension of that's the dimension of the range is 2, dimension of the range is 3, kernel is 2, dimension of the kernel here is 4, dimension of range is 1, dimension of the kernel is 5. So this is interesting too to think about, because the pre-image of 0, the only way, there's only one and only one way for the pre-image of 0 to have only one thing in it. And that is because the pre-image of 0 is a vector space in and of itself, and it has a dimension. It has to have dimension 0. In other words, it has to only be one element total. It just has to be 0 itself. The other options for the pre-image of 0 are dimension 1, dimension 2, or just to keep something going up. So you actually get all kinds of, so there is no way of getting, unless you have a small field that's binary or something, you don't, at least for reals, there's no way of getting just, of having just two things in a pre-image at all, because of this vector space structure going on here. All right, so from that comment here, the only if you have a 3 by 5 matrix, there's no possible way that this one could actually represent an injection or something that's injective, because look, the kernel itself, pre-image of 0, has dimension 2. That's clearly going to have lots of elements in it. Okay, let's look over here. These are the different distinct Smith normal form types that you have for a matrix of 4 by 2, ones down to that point. Notice this has a dimension of kernel 0, which means that this map would be injective. Dimension of the range is 2. Okay. And notice that this map is not surjective, because the where it is the codomain. The codomain lives in, well, 4 tuple land. So tuples of 4 things, so it lives in R4. So the range is 2. So the image of everything from the domain going into the codomain, it provides a dimension of 2. And dimension of 2 in a space of dimension 4, that clearly doesn't hit everything. So it's so this is not surjective. It is injective because there's no rows of zeros. I mean, no columns of zeros, but it's not. But see how there's rows of zeros? That means it's not surjective. So surjective comes, so surjective means there's no rows of zeros. Injective means there's no columns of zeros. No columns of zeros means injective. No rows of zeros means surjective. But so actually none of these then would be surjective at all. This is the only one that's injective. Okay, right here, dimension of the kernel is 1 because there's 1 0 column. Here, dimension of range is 1. Dimension of kernel is 2. Dimension of range is 0. Okay, thanks for watching.